So in this chapter, what we're going to be studying is we're going to be studying different units as well as the conversions from one unit to another. Now the first question asks, write the equality and conversion factors for each of the following pairs of units. For A, we want to convert from centimeters to meters. And so for A, we're going from centimeters to meters. And the unit conversion for that is 100 centimeters is equal to 1 meter. That's the equality. The conversion factor is written 100 centimeters is equal to 1 meter, or we can write it simply as 1 meter is equal to 100 centimeters. That's for part A. For part B, it asks to go from it goes from pounds and kilograms. So part B is we're going from pounds to kilograms. And there is 2.2 pounds is equal to 1 kilogram. Or you can say 1 kilogram is equal to 2.2 pounds. Now the conversion factor for that is 2.2 pounds is equal to 1 kilogram, or we can say 1 kilogram is equal to 2.2 pounds. Now for part C asks for pounds and grams. So we're going from pounds to grams. And 1 pound is equal to 454 grams. That's the equality. The conversion factor is 1 pound is equal to 454 grams, or we can write the reverse as we've been doing so far. 454 grams is equal to 1 pound. For D, it asks for milliliters and liters. So for D, we're going from milliliters to liters. Milli is short for millennium or 1,000. So there's 1,000 milliliters is equal to 1 liter. Now how we write the conversion factor for that is there's 1,000 milliliters is equal to 1 liter, or, I don't know why I keep writing equals there, or 1 liter is equal to 1,000 milliliters. And the last one, part E, asks for, we're going dimes and dollars. So E, we're going dimes to dollars. And as we know, there's going to be 10 dimes is equal to $1. The conversion factor for that is 10 dimes is equal to $1. Or $1 is equal to 10 dimes. In this problem, what we're going to be doing is we're going to be doing a lot of conversions. And we're going to be doing conversions within the metric system such that we can become more comfortable with the metric system and how to convert from one unit within the metric system to a completely different unit within that metric system. And so the problem reads as such. Use metric conversion factors to solve each of the following problems. So the first one, A, what we want to do is we want to convert 800 milligrams into grams. And there's a couple ways in which we can do this. All right. One of the ways we can do this is we can take 800 milligrams, turn that into a fraction, and then use the conversion factor of 1,000 milligrams is equivalent to 1 gram. And what happens is our units of milligrams cancel, and the only unit we have left is the gram. And so this becomes equal to 0.800 grams. Now there's another way in which we can do this, is we can take the 800 milligrams and realize that if we move the decimal point 3 places to the left, so 1, 2, 3, that's going to give us the exact same numbers we got before. So 0.800 grams. All right. Now, we're going to do part B. All right, just give me a few moments to get this erased. The nice thing about the metric system is that all you're basically doing is just simply moving the decimal point. That's all you're having to do. So what you need to memorize is the order of those prefixes. All right, and so that's one thing you're certainly going to want to be able to do is memorize those prefixes. For the second part, what we're going to be converting is we're going to be converting deciliters into milliliters. Just to let you know, there are 10 deciliters in 1 liter. So for part B, the question reads as such. A glass of orange juice contains 0.85 deciliters of juice. How many milliliters of orange juice is this? So we start with what we have. So make the period a little bit bigger. Deciliters, and we want to convert this into not liters, into milliliters. All right? And so we're going to start with the number we have been given, deciliters. And we're going to use our conversion factor of there's going to be 100 milliliters is equal to 1 deciliter. So our units of deciliter cancel, and what this equals is 85 milliliters. The other way we can do this is we start with the 0.85 deciliter, and we realize that there are 100 milliliters in 1 deciliter, so we move our decimal point 2 places to the right, because the unit of milliliter is smaller than a deciliter, so I know I need to move my decimal point to the right such that I get a larger number. And this is going to equal 85 milliliters. Now, I know in some schools you're taught just simply moving the decimal point. That's how I was taught back in the Stone Ages, because I am that old. But when I went to college, they taught me the first part I showed you, basically putting things in terms of fractions and memorizing what those conversion factors are. And I've kind of gone to that way now because I for whatever reason, I seem to make fewer mistakes doing the first one than I do trying out that second procedure. Let's grab another color here. Oh, grab pink. That happens to be my daughter's favorite color. So for part C, it says a package of chocolate instant pudding contains 2,840 milligrams of sodium. So 2,840 milligrams. And what we want to do is we want to convert this into grams. So we're going to convert this into grams, realizing that there are 1,000 milligrams in 1 gram. So 2,840 milligrams, I'm going to make that into a fraction, all right, and multiply. Now we're going to use our conversion factor, knowing that there's 1,000 milligrams in 1 gram. And so this gives us a number of it's going to give us number 2.84 grams. Or we can do it this way. We can start with the 2,840 milligrams, realizing that the gram is 1,000 times larger than the milligram, and so we move our decimal point over 3 places, and this gives us 2.840 grams. All right? Either way is fine by me. Whatever works best for you, however you understand the stuff is going to be perfectly fine. I prefer the first method just for myself, but if the second method is better for you, by all means go ahead and use that. You get the same number either way. Now for the next problem. Sorry, I have to look at my notes so I don't make any mistakes, but I do make mistakes. The next problem asks, once again, we're going to be using conversion factors and each of the following clinical problems. So now we're going to look at some problems that you may actually face in the real world. So the first one is number A. That green shows up nice. Number A says, let's see, the physician has ordered 1 gram of tetracycline to be given every 6 hours to a patient. If if your stock on hand is 500 milligram tablets, how many tablets will you need for 1 day's treatment? All right. So what the doctor ordered was 1 gram of the medicine every 6 hours. All right, that's what the doctor ordered. However, the tablets that you have, so 1 tablet is 500 milligrams. Well, I'm going to show you kind of an easy way to solve this. Now, the first, so you want to know how many tablets are going to be given throughout the day in a 24-hour period. All right? And what the first thing I'm going to do is we're going to convert the milligrams into grams. And so the unit I want to get canceled out is going to go, so we want to get rid of the milligrams. So we know it's 1,000 milligrams is equivalent to 1 gram. All right? And what that does is it's canceled out the unit of milligrams as well as the unit of grams. So now we know the number of tablets every 6 hours. All right? Now we want to know the number of tablets per day. So down here we'll write 1 day, and how many hours are there in a day? There are 24 hours. So what that does now is that the hours cancel with the hours, and the units that we have here, I'm going to circle this just so you see it really well, is we have tablets per day, which is what we want to know. And so if you go through and do this calculation, this is equal to 8 tablets. Oops, I can't spell tablets. Per day. So the patient is going to have to take 8 tablets per day if you have 500 milligram tablets and the doctor orders 1 gram of medicine every 6 hours. And so this is like I said, I tend to do these problems setting up the ratios just because it makes it a lot easier. And don't forget to write those units. Those units are extremely important because what those units do is they basically give you the roadmap as to where you need to go. And that's the really nice thing about writing the units that way and trying to solve the problems that way. All right, the next problem states an intramuscular medication is given at 5 milligrams per kilogram of body weight. What is the dose for a 180-pound patient? So now this problem is going to be a little bit problematic simply because we're dealing with the metric system and the English system. First thing I'm going to do is I'm going to write down the information that's given to me. So 5.0 milligrams per kilogram of body weight. All right? And what we're looking for is we want to know what dose would be required for a 180-pound patient. So what I'm going to do is I'm going to convert the kilograms into pounds. All right? So we know that 1 kilogram is equivalent to 2.2 pounds. All right? So now our units of kilograms cancel. Excuse me. We know our patient is 180 pounds. And so we're going to multiply it by the 180 pounds and just make that 1. And so now our pounds cancel. And what we're looking for is we're now looking for the mass or the amount of medication for a 180-pound patient. And that's going to equal 409.1 milligrams of the medication. Now for part C, the third part of this problem, it states a physician has ordered 0.50 milligrams of atropine intramuscularity. If atropine were available as 0.10 milligrams of solution, how many milliliters would you need to give? So the doctor has ordered 0.5 milligrams of the solution. However, the solution is going to be 0.1 milligram per milliliter. All right, so we want to know the volume. If we take the amount that the doctor has prescribed, milligrams, and we divide that by our solution, 0.1 milligrams per milliliter, what happens is that the milligrams cancel, and the units that you have, I'll write out the number. So 0.5 divided by 0.1 is going to give us 5. Now this is going to be over 1 over a milliliter, because that's what we have in the denominator. Now an inverse of an inverse means that the milliliter moves up on top, and so this becomes equal to 5 milliliters. All right? So what you have to give the patient is 5 milliliters of a 0.1 milligram solution. All right? Just a couple more problems to do out of this chapter. But these conversions become very important, right? I mean, you certainly don't want to give a patient the wrong amount of medication. You hurt the patient, be out of a job. More importantly, as I mentioned, you'd hurt the patient. That's certainly not what we want to have happen. All right. Let's see. Get that all nice and clean so you can see my ugly mug. All right. Let's see, next problem we have. So here's another problem we got. What is the density of the following solution? So let's just do a quick review about what density is. Density, a lot of times given the symbol D. In the old days it was given a Greek symbol rho. But what density is equal to is going to be equal to a mass divided by a volume. All right, very simple. Mass can be in grams, volume can be cubic centimeters, milliliters, but this problem states that they want the density in grams per milliliter. So we want to put this in the units of grams per milliliter. Right. So first one, we have a 20 milliliter sample of a salt solution that has a mass of 24 grams. So for A, we have a volume equal to 20 milliliters and a mass equal to 24.0 grams. So our density is going to be equal to the mass divided by the volume. So the mass in this case is going to be 24.0 grams divided by our volume, which is going to be now 20 milliliters. And so we go through and do this arithmetic, and what we end up getting is 1.2 grams per milliliter. So that's the unit that we have. All right, let's look at the next problem. Once I get this erased. I'll just leave this up here on top so you can just get referred to it. So part B says a solid object has a mass of 1.65 pounds. Uh-oh, we got to go from the metrics or from the English system to the metric system, and has a volume of 170 milliliters. Now, we know that the mass is going to be equal to 1.65 pounds, all right? And the volume is going to be a 170 milliliters. So we've got to convert this mass into grams. Oops, I'm sorry, this is for the second part. And so 1.65 lb, so that's pounds. Now if you remember the conversion, 1 pound, is equal to 454 grams. Make that too large. We do that quick arithmetic, that equals 749.1 grams. Now, our density is going to be equal to now our mass divided by the volume. So that's 749.1 grams divided by 170 milliliters. And that comes out to 4.41 grams per milliliter. All right. So the conversion from the English to the metric system I always think is a little bit more difficult because you got to memorize those numbers. There's so many different numbers That's why the metric system is so nice that you don't have to remember any numbers. All you have to simply do is just move the decimal point either to the left or to the right a certain number of times. And that's why the metric system is so nice, and that's why the scientists, as well as most of the world, use the metric system, because the conversions are so much easier than it is in the English system. All right, let's look at part C. Part C asks for, it's a little bit different here. In this case, we have a volume displacement, so we have to do a displacement. So a gem has a mass of 4.50 grams. When the gem is placed in a graduated cylinder that contains 20 milliliters of water, so you have a graduated cylinder, you put the gem in, and then the volume is going to change. The volume rises to a level of 21.45 milliliters. So the mass of the gem is 4.50 grams. Now it's the volume, right? This gemstone is not going to have a uniform shape. It's not going to be something that's very easy to measure its volume. And so the volume of the gemstone is going to be equal to the volume final. That's going to be with the graduated cylinder, the water, and the gemstone, minus the volume initial. That would be just the graduated cylinder and the water. So the volume of the graduated cylinder with the 20 milliliters of water and the gemstone, as I stated, is 21.45 milliliters, minus the initial volume within the graduated cylinder, which is 20.0 milliliters, which gives us a volume of the gemstone is 1.45 milliliters. All right. So now we're going to find our density, and that's going to be our mass, which is 4.50 grams, divided by our volume, which is 1.45 milliliters. And so the volume of that is, of the gemstone, is 3.1, make that point a little bigger, 0.03 grams per milliliter. That volume displacement is a really nice trick to use when you have something, a shape of an object that is not uniform. It's really nice to have that. And you'll see that volume displacement. So for instance, if they're looking at a body mass index of somebody, they would submerge somebody into water to get the volume of the individual, because the human body is not, square or rectangle or a triangle, so there is no easy formula to calculate the volume of the body. And so displacement is used quite a bit to get volumes of irregular shaped objects. And the very last problem in this particular problem states that a lightweight head on the driver of a golf club is made of titanium. If the volume of the sample of titanium is 114 cubic centimeters and the mass is 514.1 grams, what is the density of titanium? So we start with the mass. This is part D. The mass is going to be equal to 514.1 grams. All right, it's the grams. The volume is equal to 114 cubic centimeters. Now remember that 1 cubic centimeter is equal to 1 milliliter. So now our density is equal to the mass, which is 514.1 grams, divided by our volume. Now if 1 cubic centimeter is equal to 1 milliliter, then the volume here is equal to 114 milliliters. And so we go through and do this arithmetic, and it comes out to be 4.51 grams per milliliter. Now, this is also going to be equal to 4.51 grams per cubic centimeter. Right? This ends our problems of doing unit conversions. If you happen to have any questions, feel free to ask me.